All right, everybody. Today we're going to be talking about polar area. So far what we've done is we have done area in rectangular, and just kind of like as a quick refresh of what we did with the area with rectangular. If we had a function, what we did in chapter 4 was we broke it down into different rectangles, and we found the area of these rectangles by saying the height of each rectangle is going to be f of x at whatever interval that's going to be. And then we said the thickness of each rectangle is dx. So, and if calc lecture is the most entertaining part of your day, that is awesome. So not depressing, that is just so awesome. Thank you. I want to say some house points for that. So anyway, we found the area as the integral of all the heights. So this is our height, and then times the width, because it's a rectangle. Height times the width, the integral of f of x dx, and then we said from A to B. Now, if I want to take something in terms of polar. So remember, a polar function is not created in the same way as a rectangular function. Polar function, we start off, let me change colors so you can see this a little bit better. We start off at a certain angle, and then that angle produces the graph like so. It looks like I'm sort of trying to create a form of limacone. I'm not sure. I guess that's cardioid. So the polar area is created that way. So what ends up happening, and I'm going to create all these different angles, or I'm going to reach out angle by angle. What I'm going to do is zoom in on kind of like one portion of what we're talking about, just some theta. And we are going to make theta get smaller and smaller. So really, we are now doing a bunch of, you want to call these rectangles. They're not exactly rectangles because they go to a common point. What they end up being is a bunch of sectors. So if you remember from pre-calculus and all the fun that you guys had last year, I can't remember what the acronym right now you guys had. Somebody type it in for me so I can read it off. What was it? PTDD. I think that's what you guys were referencing yesterday. Anyway, the area of a polar sector is 1/2 theta r squared. PTDD. There you go. 1/2 theta r squared, where the reason why it's r squared is 1/2 theta and then radius times radius. Now, what's going to happen is we're going to assume these certain radii are going to be the same length because we are going to squeeze it so that theta ends up getting smaller and smaller. So our theta becomes our d theta. And this is where I'm going to go ahead and reference the first link on off of the Canvas webpage. So if we type in any different function here, let me go ahead and play it. Right now it's just 1 plus sine of t. Just assume this is theta. The guy that I stole this off of, I mean, when he uses GeoGebra, I kind of looked at both GeoGebra and Desmos to see which one was going to be the best. GeoGebra requires you to have everything in terms of t. Now, if you remember, all of these are parameters. So all the stuff we do in polar is still a parameter. So in essence, it really doesn't matter. What we do is we are creating larger and larger sectors, which cause this area. If you see that area goes from like a smaller value to more and more, I guess, from one value to a more and more accurate value, the more sectors that we create. So with that in mind, we are now going to take 1/2 times the integral. We are going to say from theta 1 to theta 2. We can still call that A and B. I guess you can't see that thing. Hold on 1 second. There you go. We're going to say 1/2 the integral from theta 1 to theta 2, where theta 1 represents this theta, or at the beginning theta, theta 2 ends up representing the final theta. We're going to go ahead and say r squared, but now the theta, each theta really, we're taking the limit as theta approaches 0 or d theta approaches 0. That's where we're going to create our same formula, 1/2 r squared d theta. So nice thing is it translates pretty nicely from, or for that idea of a polar area. So the rest of this is the application, which is going to be based off of what all the different graphs look like. And we really have to understand how those graphs are created. So I know it's kind of like annoying to kind of re-reference all those different polar curves that you guys discussed last time, or that we discussed last time. We're going to find we're going to look at each polar curve individually and say what is happening with that curve so that we can explore what the question is asking us to find. So the first question is, find the area enclosed by one petal of 4 cosine of 3 theta. And I actually pre-graphed all of these just so that it saves us a little bit of time. Yes, I know. Thank you. So I pre-graphed these just so. Oh, gotcha. If I check the trace and I plot that path. Try that one more time. Trace. I still want to plot the path. There you go. All right, so if I want to find the area of one petal of this, I do want to understand how this graph is being traced. This is where I want you to use your graphing calculator, use your Inspire to help you understand the graph. Now, one of the things I'm going to point out is we should have known that this is going to be a rose curve just because it's 4 cosine of 3 theta. The fact that it's cosine of 3 theta means this initial petal should be around the polar axis, or what we knew as the x-axis. If this were a sine, we would see that symmetry over the theta equals pi over 2 axis. So let me see if I can move that. It's not allowing me to. Okay, whatever. So if you notice that it's 3 theta, which means we should only see 3 petals. And as we continue to trace, we should be able to see that as well. Our goal is to find the area between one petal. So in order for us, let me go ahead and sketch on this. Let's sketch the cosine curve. So it looks like, oops, a little too wide. Let's try that again. Going to look something like this. Very, very badly drawn, and I'm sorry. Yeah, that's okay. That's driving me nuts. I can't do it. So we have one petal here. We have one petal. Again, very badly drawn, but I'm going to focus primarily on this petal. So one of the things we need to know if we're going to find the area of one petal is we need to know where the radius ends up being 0, because each petal is occurring where that radius equals 0. The first thing I'm going to do is say, where does r equal 0, which is 4 cosine of 3 theta. So 0 will end up equaling the cosine of 3 theta. And where does cosine equal 0? So 3 theta is going to equal 0. Sorry. 3 theta will equal the inverse cosine of 0, which would be pi over 2, 3 pi over 2. And because this is a 3 theta, we need to take this out. We need to take this out 2 more periods. So that's going to be at 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2. So that when we divide everything by 3, we're going to get pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, 9 pi over 6, which is 3 pi over 2, and 11 pi over 6. So going back to the tracing here, if I look to see, okay, where are all of my curves hitting 0? We can see this initially. Our first one should be at pi over 6. And if we take pi over 6 as a decimal, 3 divided by 6 is 0.5, so that makes sense. We now have the radius equaling 0 at 1.57, which is the pi over 2, et cetera, et cetera. The reason why we went out a total of 3 periods is because of this, that 3. Just trying to think what the proper terminology of it. In our pre-calc book, we talk about that being omega, which is very closely related to the frequency. But because we have 3 wavelengths occurring in a normal cycle, that's why we have to go out 3 different periods. But then in the end, when we divide by 3, we get it between 0 and 5. So good question. Now, what we could do is if we want to have fun, we could say, wrong tool. We could say the integral from 0 to pi over 6, and bad notation, but I don't care, plus the integral from pi over 6 to our next pi over 2. Now, the one thing that we have to be careful of is if we go from 0 to pi over 6, then from pi over 6 to pi over 2, one of the things you'll notice is, and we can see it up here, remember this is r comma theta. If you notice, the radius is negative. So if I add this, this is going to be a negative value. And because that's a negative value, I would really have to subtract this and then add where my radius is positive, which would be the integral from pi over 2, the next intersection, which is 5 pi over 6. And I can continue this out to add all the different petals if I wanted to find the total area. But my goal is, hey, we just want to find one petal. If we want to find one petal, let's figure out the most efficient way of doing this. One petal, this kind of goes back to a lot of the questions that people had yesterday. If I look at this petal, which I'm highlighting in the teal color, this, it's going to be efficient if this is theta equals 0, and then this angle right here is theta equals pi over 6. What if we decide to use this angle as negative pi over 6? So rather than doing all of that to find like a bunch of the total area, why don't we say the integral from negative pi over 6 to pi over 6 and go from there. Now, because I can, I'm going to shorten this and kind of move it over the side just so that I can work a little bit more efficiently. I do want to kind of like make that a little bit smaller. Okay, so let's say the integral from negative pi over 6 to pi over 6, and we will say 1/2 that integral r squared, and we know that r is 4 cosine of 3 theta squared d theta. I hope everybody is with me on this one. And then how do I integrate that? Well, I can go ahead and use a calculator, but that's not fun. Let's go ahead and do this one by hand, and then we'll use the calculator to check us at the end. There was a good question. Could we do 2 times the integral from 0 to pi over 6? I was actually going to get to that, and I'm going to encourage to do that. So what that reference was is if I take a look at this half petal, it's going to make life a lot easier for us. Now, visually, what you should be able to see, and I'm going to use the mouse here, visually, you can see that we have the symmetry over the polar axis. That symmetry over the polar axis actually translates to this is an even function. And because it's an even function, we can go ahead and double and say twice 1/2, and then go from 0 to pi over 6 for cosine 3 theta squared. I'm actually going to erase that just because I'm not sure why the mirroring just ended. Hold on 1 second.
Wait, if you did what Jacob said, wouldn't that result in a negative area? Or like...
Actually, we are going to have to do this more often than not. Great question. We're going to have to do this a lot just because we need to understand what's happening, or at least how to avoid negative radii. So going back to your question, would this result in anything negative? No. It's going to be important for us to make sure we know where the radii are positive and where those radii are negative. So, wrong tool again. So this aspect, the fact that I would have to subtract that actually, the fact that I have to subtract that to find a positive area is purely because the radii are going to be negative right there. So one question that was asked that I can address right now, how can you choose your interval? We could actually say this interval from negative pi over 6 to pi over 6 if we want to include that region. What we could say is we could take the opposite of that region if we go from negative pi over 6 to, or from pi over 6 to pi over 2. If I wanted to work with this region, that would be from pi over 2 to the next interval, which is 5 pi over 6. So we have lots of choices if we want to find the area in one petal. The easiest one tends to be those that are centered around 0 or around 0, because anytime you plug in 0, you tend to have some nice values. Thank you. So what I'm going to do here is I'm going to go ahead and make this 16 cosine squared of 3 theta d theta. So I doubled the interval. So I doubled the interval going from 0 to pi over 6. So all those rules that we learned earlier are still going to apply. And now, how do I work with this without a calculator? This would then be the integral from 0 to pi over 6. And that would be 16. And if you remember a power reducing formula would say cosine squared of theta would be equal to 1 plus cosine of 2 theta all over 2. So we would turn that into 1 plus cosine of 6 theta all over 2 d theta, which, let me go ahead and use this space, gives us 8 times the integral from 0 to pi over 6 of 1 plus cosine of 6 theta d theta. If we integrate that, we will get 8 theta, and the integral of cosine is sine, so it would be plus, and don't forget to divide by that 6, 8 6 sine of 6 theta from 0 to pi over 6. And now going back to Jacob's suggestion earlier of going from 0 to pi over 6, I think is definitely a much better improvement than having to plug in negative pi over 6 to pi over 6. The question that was just asked is when do we consider a negative area? The negative area occurs, and if you, let's go ahead and look at right here. If you look at this graph, right now all of my radii are positive. So as I scroll, as I continue to scroll, if you notice, all of these radii are now negative. Because these are negative radii, what's going to happen is this would create what we call a negative area as opposed to the positive area. And just a second after I'm done working with these, I am going to go to the calculator. And using the calculator, I will show you that we are going to end up getting some negative values instead of positive values. Or I'm pretty sure we're going to get some negative values. Let's go ahead and finish working this out. So 8 times pi over 6 ends up giving us 4 pi over 3. And then the sine, if we plug in the pi over 6, the sine of 6 pi is 0. So 4 pi over 3 plus 0, and then minus 0 plus 0. So that suggestion is going to be, that suggestion going from 0 pi over 6 is a really good one. So we end up with 4 pi over 3 as our answer. Kind of like using some of the calculator skills, if you notice, I have this saved as R1. So I'm going to go to this screen, do a shift plus. If I say going from negative pi divided by 6, and I go to pi divided by 6, and I'm going to say 0.5. Actually, let's make it 1/2 so we can see an exact value. 1/2, and then our radius was 4 cosine through, actually, this is why I wanted to do R1. And then d theta. Yeah, let me see if I could make this R1 of theta. I'm not sure if that's going to correct it or not. I'm really hoping so.
Huh?
And I did 6 instead of 4. Nice. Try that one more time with the appropriate number in there. I have not squared it. This is one of the reasons why I do like doing it without the calculator. Let's go ahead and say R1 of theta squared. Pardon the technical difficulties. And try one more time. I don't need the 4 in there, mainly because the 4 is going to be part of the R1. All right, I finally get 4 pi over 3. Yay. Looking at the questions, so the area between every increment is a part of the graph. The area between every increment is a part of the graph. I want to say yes, if I'm understanding that question properly. Now that I have the right area in there, let's play a little bit and say what's going to happen if I take the interval from pi over 6 to pi over 2. If you remember on the curve that ended up giving us negative radius, this actually worked that we got the positive value. So what I was expecting didn't happen, but I'm glad that it didn't happen that way. If I wanted to do another portion of the curve, the next set of intervals is going to be from pi over 2 to, if I go back to what I have on the screen, the next one, 5 over 6, thank you. This should give us the exact same value. Now, next question is, what happens if I go from 0 to 2 pi? Why does it give me 8 pi instead of 4 pi?
Because the normal domain is 0 to pi. Yeah, it's double trace.
Yeah, double trace. Very good.
Good job there.
So, excellent job, Cos. So,
I mean, that was Aiden that said double trace, but okay.
I saw he had said double trace, but you're the one that actually verbalized it. So, plus I had to take the opportunity to say Cos. All right. Problem number 2. Find the area of the inner loop of 2 sine of 4 theta. So what I'm going to do is go back to my sketch pad and let's turn off the first graph and let's go to the second graph. My job is to find the inner loop of 2 minus 4 sine theta. So I'm going to go and do a trace one more time to say, when does the inner loop get created? So if I'm sketching the whole thing out, what I should see is the inner loop just got created right there. So the inner loop gets created when the radius first hits 0 up until the radius hits 0 again. So really, if I go from 0 to 2 pi, we should end up seeing the radius hitting twice. And so let's algebraically determine that. So where does my radius equal 0? which is the 2 minus 4 sine of theta. So that's when sine of theta equals 2 over 4, which is a half. So theta ends up equaling pi over 6, and then 5 pi over 6. So this is where our overall area is going to be 1/2 the integral pi over 6 to 5 pi over 6. And then our radius squared, so 2 minus 4 sine theta squared d theta, which at this point, I don't feel like there's anything that I could do to make life a little bit easier. Maybe if I said I go from pi over 6, because we know this inner loop is created first at pi over 6. We know down here is pi over 2 with a negative radius. And then here is 5 pi over 6 as we're following the curve, which going back to the parametrics, understanding how those are created, very, very important, or understanding the orientation. If I wanted to, I could double the area from pi over 6 to pi over 2. Would that benefit me? I don't know. Probably at some point it would. I'm just going to go ahead and keep this one as pi over 6 to 5 pi over 6. So
What do you have to do?
pi over 6 to 5 pi over 6. Actually, knowing what's going to happen, it probably would benefit me to go to pi over 2. So let's pretend I didn't. So let's FOIL 4 minus 16 sine theta, and then plus 8 sine squared theta, d theta. And this means that once again, I'm going to have to use power reducing formulas. So if remember, sine squared theta is going to be 1 minus, where the cosine one was 1 plus. This is going to be 1 minus cosine of 2 theta over
Mr.
2.
Beck, 4 squared is 16.
Oh, come on. I agree with you, by the way. Yep. So whoever said that and I wasn't watching, thank you. Probably like a lot of people. So 16.
It was everyone.
Yeah,
Everyone
pretty
said
much
it.
everyone.
And you said it first, though.
Anish, thank you. Let's go ahead and that'd be some, I'm trying to picture, that'd be some Ravenclaw.
Slytherin.
Is Anish Slytherin?
It is Ravenlaw. It's
Ravenclaw.
Ravenclaw. Caroline's a
Dude,
troll.
the Slytherin.
Yeah.
Slytherin minus 20 for trying to cheat.
No.
Yes,
No,
Okay,
I
okay.
actually didn't know.
Okay.
of course
right.
you didn't.
So at this point, I'm going to say 1/2. Thank you guys for, I do appreciate talking to you guys, and I missed this opportunity. If only Blue One knew exactly what happened during our class, they would be jealous. So I am going to simplify this into 8 minus 8 cosine of 2 theta. D theta. And then any simplifying I could do, I have 4 plus 8, which ends up giving me 12, and I'm going to divide everything by 2. So one final cleanup just before I do my integration for clarity. So that's where the 4 and the 8 combine into 12, but then divided by 2 is 6. 6 minus 8 sine theta, and then minus 8 cosine of 2 theta. And now that we're there, let's just go ahead and integrate. That gives us 6 theta. That the integral of negative 8 sine is positive 8 cosine of theta. The integral of negative 8 cosine of theta is going to be negative 8 halves, or negative 4 sine of 2 theta. And this goes from pi over 6 to 5 pi over 6. And as I was talking about before, if I would have gone from pi over 6 to pi over 2, then that would have made life a little bit easier for me. But I'm already here. So finishing off, 6 times 5 pi over 6 is 5 pi. Cosine of 5 pi over 6 is negative square root of 3 over 2. So that would be minus 4 square root of 3. The sine of 5 pi over 3, if we multiply that by 2, the sine of 5 pi over 3 is going to be 1/2. So
No, wouldn't it be negative root 3 over 2?
yes. So negative root 3 over 2. So we have 4 square root of 3 over 2. So that'd be 2 square root of 3. You guys agree with that?
Yeah. Wait, wouldn't it be minus? Wait.
It would be subtracting a negative.
Yeah.
Okay. I just want to make sure these are accurate for me. All right. So I have that. And then if I subtract, by plugging in pi over 6, I'm going to subtract pi, 8 cosine of pi over 6. That would be square root of 3 over 2. So that'd be plus 4 square root of 3. And then sine.
Wait,
Go ahead.
I might be
Wouldn't
wrong
4
here,
sine
but
pi by 3?
if you're carrying the 1/2 through everything in the integral, shouldn't that lead to, in the integral, have 4 cosine 2 theta, which should,
You cut out
because
there.
if you're distributing the 1/2 through the entire integral, then shouldn't you have 4 cosine 2 theta? So then your sine,
So
so
that should
then
be,
you'd get 2 sine
yeah.
2 theta.
I agree. Things weren't matching up on my end either. That's fine. Good call. Thank you. That would be some Ravenclaw points. No, those ones are actually Slytherin points.
No, that was Kalika.
No, that
That's
was me.
Ravenclaw.
That was me.
That was Kalika. That was
That was
Ravenclaw.
Klika? That actually
Yeah.
sounded like Natsume, so I apologize.
Caroline, you did not adopt me.
So some more Ravenclaw points on that one.
Oh, yeah. Yeah.
Okay. Anyway, now my notes are matching up. So I forgot to distribute the 1/2. So that would be plus 4 square root of 3. Thank you for the correction. And then minus square root of 3 on that one. You don't sound Gryffindor plus 50. All right, there you go.
50? Okay, then.
Do I have everything that I need? I think that's it. So that gives me 4 pi. Right now I have -4 plus 3, or -4 plus the square root of 3. How about -4 square root of 3 plus the square root of 3? So that's -3 square root of 3. And then I'm going to be subtracting another 3 square root of 3, so that's -6 square root of 3. And I get my final answer. All right, do I want to use a calculator to check? Yes or no? No. I might be able to make this one a little bit easier because I already have like the general setup. This time we're using R2 of theta. And we are going from pi over 6 to 5 pi over 6. Four pi minus 6 square root of 3. Trying to remember, where was the camel submission again? So many things have happened in the past 2 weeks. Oh, the chapter 6 project. Didn't I actually assign or get some points for that already? I could have sworn that I did. How about I'll check on that. Check, camel, and Slytherin. It would have been a long time ago. All right. Now we get to a little bit more of the fun one. what happens if we are going to find the area of the region inside 1 plus cosine and outside 3 cosine? So before I do anything else, do I know what that is going to look like? What does 1 plus cosine of theta look like? Anybody shout out what that is?
Wait,
Is it a
what?
cardioid?
It is a cardioid. And then what does r equals 3 cosine of theta look like? Oh, Gabriel with the win. Circle. So let me go ahead and go to the graph. Now, he probably already graphed it, but kudos to you for preempting my question. So if I go to tab, let me scroll up. Let's turn off the Lima sum, turn on the circle, and then turn on the cardioid and then the circle. Now, I do want to zoom in a little bit just because I feel like I am I'm not close enough to the action. There we go. And now, so if we want to know the region inside the cardioid but outside of the circle, so outside of the circle but inside the cardioid, what I'm going to be looking at is this region right here. So I'm going to escape. So I'm looking at this region right here. So as I look at it, I am going to draw this portion. So kind of like a little bit of a
Isn't it both the top and bottom?
It is going to be both the top and the bottom. Now, anybody want to guess what I'm doing by only drawing this portion?
I realize you're gonna double it, but like
Exactly.
I was making sure I'm making sure we were gonna double it.
We are going to double it. So the very first thing that I need to know is, where do these intersect? So the intersection is going to be, so where do these intersect? And the intersection is going to be when 1 plus cosine of theta equals 3 cosine of theta. So 1 would equal 2 cosine of theta. So cosine of theta is 1/2, which means theta is going to be at pi over 3, which based off of my drawing, that pi over 3 seems pretty accurate. Now, this pi over 3 is going to occur for both the circle and for the cardioid. Now, what's going to be a little bit different is, and I'm going to do this in red, where do they intersect right here? For the circle, can anybody tell me where this is for the circle? For the person who asked, why not 2 pi over 3? 2 pi over 3 is not where cosine is 1/2. The other one is going to be at 5 pi over 3. So I could end up with both. Now, for Gabriel asking or saying pi over 2, for the circle, this is going to be pi over 2. But for the cardioid, what is the angle that creates that one? Pi. So what this means is we are going to have to set up 2 entirely separate integrals in order for us to figure this one out. So what I'm going to do is, in red, we are going to take the entire cardioid that's going to be graphed right there. So in essence, we are going to take the cardioid which will have this shape. And then we are going to subtract out this section that came from the circle. So it'll be minus this smaller portion. And then the overall shape that's going to result is that part of the curve with this. And then in the end, we're going to double that value. So now that I have it beautifully color-coded, the area of this cardioid is going to be 1/2 the integral from the intersection point, which is going to be at pi over 3. Oh, by the way, we're going to double all of this, so these are going to cancel each other out. So I'm not going to worry about the 1/2 anymore. So pi over 3 to, we're working with the cardioid, so pi over 3 to pi, 1/2 theta r squared. So 1 plus cosine of theta squared, d theta. And then I'm going to change colors. So then I'm going to subtract out. Once again, we're doubling, so it's 2 times 1/2, so I don't have to worry about it. And then this is going to be the intersection, which is pi over 3, going to pi over 2. And then 3 cosine of theta squared d theta. And then that's going to give me my total area. And seeing as how we've taken a long time already, let's just go ahead and do this in the calculator to make life easier. So what I'm going to do is I'm going to include a 2 here just because I have the 1/2 on the outside anyway. I now want R3 ended up being the cardioid. So this is pi over 3 going to pi. And I am getting pi minus 9/8 square root of 3. So what's in red is pi minus 9 square root of 3 over 8. And then it is that idea of r squared minus r squared. Let's go ahead and now do this as R4. Do we get anything otherwise in this course? So this gives me 6 pi over 8, which would be, let me change colors to match up. 6 pi over 8 is 3 pi over 4. And then it'll be minus 9 square root of 3 over 8, which happily, change colors one more time, turns into pi minus 3 pi over 4. So that area just ends up being pi over 4. So a very, very nice, happy answer. And we celebrate. Yay. On to part 2. So on to part 2. Part 2, if I open up the, hopefully I didn't, I opened up the right one. No, polar arc length. I used pi over 3 because that is the first intersection point. Let me go back to the calculator really quickly. The first intersection point is pi over 3, which is right here. The second intersection point is actually at 5 pi over 3. And this 5 pi over 3 occurs, 5 pi over 3 for the cardioid. That 5 pi over 3 is one of the 4 intersection points of that circle. So this would be pi over 3, 2 pi over 3, 4 pi over 3, and then 5 pi over 3. So this is another reason why it's a lot easier just to double this one region. That way we don't have to work with all the different intersection points. Hopefully that answered your question well enough. Okay. Going back to this, that I just have 1 plus cosine in there. It's what comes up normally. What's going to happen is what we did before. We are now going to be taking polar areas, polar arc lengths. Our formula for polar arc length is the square root of r squared plus drd theta squared, which sort of models the square root of 1 plus f prime of x. There's not a good proof that I saw in our book for it. If anybody wants to submit that proof to me, I might be willing to throw some extra credit points to the person who first does it and does it well. Have to quantify that. But this kind of models that if we want to think parametric, this is the square root of dx dt squared plus dy dt squared. It's really modeled after that same kind of format. Yes, go Gabriel. And then the more points that I add, are really the more we're looking at this as ds. One of the things I mentioned, I can't remember last time, S ends up being kind of like an important parameter when we start talking about multivariables. To have everything based off of an arc length, it makes life a little bit more efficient. So this is kind of setting up some of that mentality for multivariable calculus next year. That's assuming we have school next year and we don't all die. So, not to be morbid, but nope. The nurse gave me a bad glare on that one. I'm sorry, guys. We're all gonna be happy.
Look, I'm not gonna die from corona. I'm gonna die from my parents killing me and my siblings. Let's be real.
Fair enough, actually.
Nobody's surviving in my house.
Death. Death is greater than school. I'm not going to acknowledge the. I'm not going to acknowledge what Natsume said. So by not acknowledging it, I acknowledge it, right? Unfortunately, I really hope that doesn't happen. I can't really see it happening in Carmel, but who knows? All right. I'm really, really hoping not. And everybody, if you guys do experience any form of racist attack, please, on I like to use the Stop It app. So going from joking and everything to serious, I don't want to see anything happen to any of you guys because I kind of like you guys. So all right, going back to this. This is where we're going to go ahead and just streamline this. I want to find the length of the cardioid, 2 minus 2 cosine of theta. So 2 minus 2 cosine of theta. Let me move this out of the way. I know you guys can't see the group chat on there. Go back to tab. I actually don't have this in there. So 2 plus 2 cos theta. You know I said it. So 2 plus 2 cosine of theta. Let's turn off the other ones. Okay, which means I'm going to have to zoom out. Let me try that one more time just to make sure I got the right zoom out. All right, let's do a trace on this one just so we can see how this is being created. Trace, path plot. Let's go polar. Nope, you didn't hear anything. So to find the length of the cardioid, we do have a couple different options here. If we go from 0 to, where are we at right there? That would be pi. So I could double the integral from 0 to pi to make life a little bit happier. Let's go ahead and do that. So actually, we could do it straight up. Our arc length is going to be the integral from 0 to 2 pi, or we could double going from 0 to pi. Square root of r squared. So let's go ahead and follow the formula if we want here. Dr squared, what is dr d theta? That would be positive 2 sine theta. So that'd be 2 sine of theta squared. And for the person who said that, you're actually,
I mean, technically it wouldn't be negative. I guess it doesn't really matter, but. Oh, wait, never mind. I was integrating, not other way around.
So we could still double going from 0 to pi. That's one of the things I actually do like about the polar, just because of all that symmetry. We can make a lot of mistakes. Although the bad thing is, if we make a mistake, we don't realize, kind of like what Mr. Beck just did. So, and then going back to 2 minus 2 cosine theta squared d theta. So let's FOIL this out. So integral 0 to 2 pi, square root of 4 sine squared theta plus 4 minus 8 cosine of theta plus cosine 4 cosine squared theta d theta. So that would be, my handwriting is getting sloppier and sloppier. Integral from 0 to 2 pi. I have 4 sine squared plus 4 cosine squared, which will give me the square root of 8 minus 8 cosine of theta. What can I do with this? Let's have a little bit of fun. And I say fun, you guys are like, yeah, I'm not sure. Excuse me. So that would say the integral from 0 to 2 pi. And then say square root of 16 minus 16 cosine theta over 2 d theta, which if we factor out that 16, that would be 4 times the integral from 0 to 2 pi. Square root of 1 minus cosine of theta over 2. And I'm not sure how many of you recognize that ends up just being from 0 to 2 pi. That ends up being the sine of theta over 2. Audie, we're all going to get infected now. Thanks. I guess that's Addie. Let's go ahead and integrate. The integral sign would be the negative cosine. The negative cosine, then we have to double it. So that would be negative 8 cosine of theta over 2, going from 0 to 2 pi. And then the cosine of pi is negative 1, so that would be 8 minus negative 8, giving me a grand total of 16. I did, Audie. So I was looking at it yesterday. Audie, Addie. And no, it's Addie, not Audie, not Addie. I have a student in my Blue 4 class who his name is Addie, and his last name is very similar to a student in this class. So, and then I work with another girl whose name is Addie. So all the Addies and Auddies kind of messing me up. So that's why. Nope, not her. I'll clap. All right, let's go through this a little bit efficiently. Find the area bounded by the curve and the x-axis. So if we kind of want to see, this is an AP problem, by the way. If we want to see how to determine this area, we need to know what that theta value is and what that theta value is. And hopefully, common sense is going to dictate that this is most likely going to be theta equals 0. This is most likely going to be theta equals 5. We can verify that to say, where does, actually, we're told that going from 0 to pi. That makes life easier. So the area bounded by the curve and the x-axis, we are going to say for part A, our area is 1/2 the integral from 0 to pi r squared d theta. This is where I normally say the AP is going to allow you to just leave it in that terminology because it has formally defined what r is. Since this topic is no longer on the AP, maybe your college courses will do the same thing. I'm not sure if IU will do that because we all know that IU is lesser than Purdue. So that's okay. No comments on that one. And then this one is a calculator problem. Yeah, that happened to some of my other students too. All right, take care. If you do have to go for it. So we can type this in the calculator. If we type this into the calculator, we will end up getting 4.382. Part B, find the angle that corresponds to the point where the x-coordinate is -2. So we would say, where does -2 equal r cosine theta? And we know that our radius is going to be, going back to what we have up here, theta plus sine of 2 theta. So -2 equals theta plus sine 2 theta times cosine. So I'm going to go to this screen, and this is a perfect opportunity to show some calculator work. So let's solve. Where does, and I'm just going to do this in terms of x because it's easier. Where does -2 equal x plus sine of 2x times cosine of x? And we want to know, I just want to make sure all my parentheses are matched up. Solve that for x. And we get the x value of -1.85. That is not in our interval. So what happens if we add 2 pi to that? That's still not what I want. So let's go ahead and take a look. In essence, we're going to want this angle. And I also kind of want to make sure my parentheses match up. That's why. So I'm going to scroll back up here. I forgot to introduce some parentheses here because that would be my R. Let's try that one more time. Now I've lost the parentheses. I think I need some right there. And there we go. And we need to get an answer going from 0 to pi. So that would be this one right here. So theta equals 2.786. For part C, we are told that drd theta is negative. What does it say about r? And that's going to be, let me do this in red. From pi over 3, which is right here, to pi over 3, we are told that drd theta is negative. What does it say about the curve? So this means that the radius is decreasing when drd theta is less than 0. So what does this say? Since the radius is decreasing, the curve approaches, I don't want to know if I want to say approaches, but I already started, approaches the origin instead of moving away. And then last but not least, find the value of theta that corresponds to the point in the first quadrant that's the greatest distance. So how do I come up with my greatest distance? What I'm kind of anticipating is somewhere around here to be that greatest distance. So this is a great opportunity to do optimization. So if you remember from 0 to 2 pi, or not 0 to 2 pi, but 0 to pi over 2, which is what we're looking for. We need to know where is dr d theta equal to 0. So where's our derivative equal to 0 so that we establish our critical numbers. Once you know our critical numbers, then we're going to compare them to endpoints. So what I'm kind of looking at here is when theta equals 0 and when theta equals pi over 2 are going to be my endpoints. And then I need to know where drd theta equals 0. So going back to my radius of theta plus sine of 2 theta, theta plus sine of 2 theta. What's the derivative of this with respect to theta? That would be 1 plus 2 cosine of 2 theta. So where does that equal to 0? So 0, let me write it. And as you can tell, I'm trying to go faster now. So where does the cosine of 2 theta equal -1/2? 2 theta is going to be at 2 pi over 3, and I can include 4 pi over 3, but when I divide by 2, I only get 2 pi over 3. So now I establish what is r of theta, what is r of 0? R of 0 ends up being 0. R of pi over 3, if I plug this into the calculator, will give me 1.913. And r of pi over 2 ends up being just pi over 2, which is 1.571. So the answer is when theta equals pi over 3. I'm going to go ahead and turn off the recording at this point, and I will end